Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
I'm Madan Muswati from the Research in Software Engineering Group, and it's my pleasure today to introduce Naghmeh Ghaffari from University of Waterloo. She's actually in University of British Columbia at Vancouver right now. She did a PhD at University of Waterloo. She's actually very broad in her interests. She started out as an electrical engineer working in control theory, and right now she's working on analysis of concurrent and distributed systems. And today's talk, she'll be talking about analysis of infinite state concurrent systems. Naghmeh?
Thanks, Madan. So, as Madan just pointed out, today I'm mostly going to talk about the algorithmic techniques for the analysis of concurrent systems. Just a broad introduction. So in recent years, we know that most of the concurrency is becoming commonplace in application software. There are several reasons for this. One of the main important thing is that software is playing an important role in our daily life, and so the number of tasks we want to be achieved by the software is increasing, and so the complexity of the software. The other main reason is that due to power consumption limitation, the processing power of the chips is not going to grow as expected by Moore's law anymore. So multi-core processors are in high demand in recent years. That means we need to implement concurrent software to run on these multi-core processors. So what is a concurrent software or concurrent system? Basically, it's a collection of processes. Each of them is a sequential thread of execution. So if we are assuming all of these orange bullets are a process or a thread of execution, then they either communicate through a shared data structure, or if they are in a distributed manner, they usually communicate through a bunch of communication channels. Debugging concurrent software is very hard. First of all, concurrent software is error-prone because it's due to non-deterministic interaction between concurrently executing processes. There are common issues with concurrent software, which is data races, deadlocks, and live locks. It's hard to detect bugs in concurrent software because they only happen sometimes. It's hard to reproduce them because most of these bugs are appearing because of the particular scheduling decisions, and it's hard to eliminate them. Two general approaches to debug concurrent software is using dynamic analysis or static analysis. So in dynamic analysis, the approach is based on dynamic analysis. Information is being collected during runtime, and then this collected information is being analyzed to see if an error has occurred, and then usually apply a recovery procedure, sometimes rolling back the whole system to a correct state. The advantages which come from the approaches based on dynamic analysis is that we analyze the actual runtime behavior of the system. It's precise. We don't need abstraction or over-approximation of the execution of the system. However, the main disadvantage is that usually the conclusion we get from the approaches based on dynamic analysis do not generalize to future execution. On the other hand, static analysis builds a model of the state of the program and keeps track of all possible states. So using these approaches, we can prove that software behaves correctly for all inputs and in all executions of the system. However, since it's impossible to basically analyze every execution of the system, we need to do some sort of abstraction or over-approximation of the state of the program. That means if we do detect an error using static analysis, if it's based on over-approximation, we're not sure if this error has been introduced because of the over-approximation or if it really exists inside the system. So during my graduate studies, I've been basically working in both of these main domains. During my master's, I mostly worked on the dynamic analysis of concurrent systems. I looked at monitoring of distributed systems, collecting information during execution, and I particularly looked at state inconsistency problems in distributed systems. The main idea behind my analysis approach was basically using some techniques from signal processing and do some sort of statistical analysis to be able to analyze the collected information during the runtime execution. However, during my PhD, I moved to static analysis of concurrent system. I started looking at mostly the algorithmic techniques for the analysis of concurrent and distributed protocols. Today, I'm mostly going to focus on the static analysis and the work I did for the static analysis of concurrent systems. Well, model checking is a familiar word, I think, for everybody in this room. So it's a prominent automated technique for the analysis of finite-state concurrent system. So what does a model checker do? We want to check, using a model checker, if a particular software or hardware artifact satisfies a correctness property. To do that, first we have to extract a model from the artifact. This model should be finite, but usually that's not the case, so we need to use some sort of abstraction techniques to derive a finite model. Then we have to translate the property of interest to usually a temporal logic formula, and this finite model and the formula are inputs to the model checker. So model checker usually produce a yes or a no answer to say if the property is satisfied by the software or hardware artifact. The main advantages of model checking is, first of all, it's automated, and it generates a counterexample if the property is not satisfied by the system. The main disadvantage, state explosion problem. So programs may have a very short textual description, but they may have infinite state spaces. In addition, the limitation of model checking to just finite state system excludes lots of interesting programs for which the model checking approach is applicable to. For example, we know that many concurrent systems, they generate infinite state spaces. So communication protocols, they usually communicate through a bunch of unbounded channels. This is a source of infinity for the state of this sort of system. Or cache coherence protocols. We don't know how many number of the processes are participating in a cache coherence protocol, so that's another source of infinity in a concurrent system. Unfortunately, analysis of concurrent system is very hard. Most interesting properties are undecidable for sufficiently expressive classes of infinite state models. In high level, there are two forms of analysis of concurrency of infinite state models. One is first identifying a subclass of the whole general problem to see for which the problem becomes decidable. The other is coming up with a bunch of semi-algorithms based on induction or abstraction that they scale to realistic examples. However, they usually over-approximate the program, and we can do only conservative analysis for this system. Yes?
So would you say that concurrency and infinite stateness, they're orthogonal issues?
No, not necessarily every concurrent system is infinite state, but many important concurrent systems are infinite state.
I see. So, but for example, your focus is on infinite state systems,
yes,
even for sequential programs, or just the infiniteness that is because of replication in concurrency?
My focus is on two parts. Well, infinity because of the communication channel size. The other, the unbounded number of processes participating in a protocol.
Okay.
So, focus of my research, basically algorithmic analysis techniques for concurrent and distributed system. I have looked at two common models of computation for concurrent and distributed protocol. One is FIFO system, the other is parameterized systems. However, both of these systems have infinite or unbounded state spaces. What is a FIFO system? First of all, it's a bunch of finite state machines that communicate over unbounded perfect FIFO channels. This is an example of a FIFO system consisting of three processes. Each of them has been shown by a finite state automaton. They communicate through three channels. One thing to note in here is that in FIFO system, the transitions of the automata are labeled by a set of actions. These actions are either a write, a read, or a conditional action. For example, in this automaton, the process would go from state 1 to 2 by writing letter A on channel 1. It would go to from state 2, it would go to state 3 by if letter B can be read from channel 2. And a conditional action, which looks like this, says that this process would go from state 1 to 2 if letter A can be read from channel 1, and during this transition, letter B is going to be written on channel 2 atomically. Both of these actions appear. FIFO systems are Turing powerful. Just having one single unbounded channel is sufficient to simulate the tape of the Turing machine. The other model I looked at was parameterized system. So a parameterized system is a family of systems in which n processes execute the same program concurrently. This is an example of a parameterized system. So, for example, these models are used to model lots of distributed and concurrent protocols, such as cache coherence protocol, mutex algorithm, resource sharing protocols. And we want to check, when we talk about correctness of parameterized system, we want to check that the property holds for every size instance of the system. For example, if we have a mutex algorithm, we want it to be correct independent of how many number of processes are participating in the protocol. Similar to FIFO system, verification of parameterized system is also undecidable in general. For the rest of my talk, basically I divide the rest of my talk in two parts. First, I will talk about FIFO systems and the contributions I had towards the analysis of them, and then I would move to parameterized system analysis.
So in this last one, can't you just, I thought that there was some reduction where you reduce it to Petri nets, where you have this counter abstraction for each state. Is there something like that?
Similar to that. I'll talk about it later at the end, towards the end of the talk. One of the ways to analyze parameterized system is reducing it to Petri nets and use counter abstraction. We have a similar approach, but somehow different.
But you said that the reason I was asking is that you said that it is undecidable, but Petri net coverability is decidable, right?
But that's one model of it. So in general, for example, if you have a ring of processes, unbounded number of processes in a ring, and if you allow just one bit of information in the token that goes through the ring, the problem becomes undecidable.
I see that.
In a very high level, yeah.
So one bit of information in the token. So the token
Yes.
has a color. So what do you mean
So-
by a bit of information?
So that was one instance of why the problem becomes the undecidability. For example, if you have a ring of processes, you don't know how many processes are in this ring, and these processes only communicate through a token. The token can go either right or left. And if you just add one bit of information, like the color inside that token, the problem becomes, it's reducible to a halting problem of Turing machine. So I will start the analysis of FIFO system by just explaining an example. This is an example of a FIFO system with two processes, process 1 and process 2, communicating through two channels, channel 1 and channel 2. We want to check if the error state, which is state 3 in this particular example, is reachable or not. In the initial state, the global state of the program is saying that both of the processes are in control location 1 and both channels are empty. In a possible execution, process 1 would go from state 1 to 2 by writing letter A on channel 1. Then process 2 can basically read this letter, go to state 3, and by reading letter A, it will write letter D on channel 2. And while sitting at state 3, it can keep writing letter D on channel 2. As you can see in this particular execution, the error state is not reachable. Now, looking at an alternative execution, again, both processes start at control location 1. Both channels are empty. Then letter A is written to channel 1. However, this time, process 2 would actually read letter A and take this transition and go to state 2. Writes letter B on channel 2. Then, going back to process 1, we can see process 1 can read this letter B and goes from state 2 to 3. And we can see in this particular execution, error state becomes reachable. We are interested in reachability problem in FIFO system. That means we want to see, given a FIFO system and a set of initial channel configuration, we want to compute the set of all global states reachable from this initial channel configuration. To do this, we said FIFO system consists of a bunch of finite state automaton. So we have to first combine all of these automata and compute a cross-product automaton. then for each control location of this cross-product automaton, we need to compute all possible channel configuration while the process is sitting in that particular state. Before explaining how we can do this, let me define the semantic of actions in our system model. If we assume W is in sigma star, we define application of action read of A to W by removing letter A from W, applying write of A to W by concatenating letter A at the end of W, and if we apply two actions X and Y to W, first we apply X to W, and then we apply Y to the result of X to W. So, going back to the problem we are interested in, which is reachability. We want to compute the set of all reachable configuration of this FIFO system, represented by this, the control locations of it represented by this automaton, and the initial channel content is I. We said in order to do that, we need to compute the set of all reachable channel configuration at each control location of this automaton. In order to do that, first we construct an automaton by making state 1 as the final state. Then we apply the language of this automaton, which is A1, to I. The result of this would give us all reachable channel configurations while the FIFO system is sitting at control location 1. So now, if we want to compute the set of reachable configuration at 2, we would construct another automaton by making state 2 as the accepting state. Then we apply the language of this automaton, which is this expression, to the initial channel configuration. Similarly, to compute the set of reachable channel configuration at control location 3, we would construct automaton A3, and the same for A4. So again, going back, the problem we are interested in, reachability. We reduced that problem to computing the result of this, basically applying a language of action to an initial channel configuration. Looking at this expression, we see we do get repeated application of a single action, which is, for example, read of D star, or repeated application of a language of action or a string of actions, such as read of C followed by write of A star. Computing this, that means the result of read of D star to I, is relatively easy. However, computing the result of an action language, basically a language of actions, repeated application of a language of actions to an initial channel configuration is not easy. And I'll show this. So in order to do that, first, we define this new problem, which basically we reduce the reachability problem to this problem. We call it limit language problem.
Can you go back to the previous slide?
Yeah.
How do we get the answers to these? Is this a straightforward?
That's the problem we want to solve.
Oh, okay. So
That's actually, so for reachability, we started from reachability. We reduced the reachability to basically calculating the result of this.
Madan, are you asking how did you get from the figure on the left to...
Yes, exactly.
Oh,
the thing on the
okay,
right?
so this is,
That's a different question. Yeah.
okay, sorry. So for example, let's see. This is an automaton where one is accepting state. What's the language of this automaton? Read of D star.
Okay. And
So-
I is
I is the initial channel configuration. That means we say, okay, I want to say I want to compute when the process is sitting at control location 1, what are the possible channel configuration? I'm sitting there. I'm not moving forward. And then, for example, if I want to do it for 2, I construct a new automaton where 2 is the accepting state, and I apply this language, which is read D star followed by read A and this loop. And then I see what are possible channel configuration while the process is at 2. And I do that for every state in the control locations.
And that process is straightforward to do?
So no, so actually that means first we reduce the reachability to the problem of computing these equations, basically.
So like if there are multiple cycles here, I mean, I can
That
see
language becomes, exactly, the language becomes more complicated, and that's
But
why
it's
the
still
problem
a regular
is,
expression.
it's a regular expression of actions.
I mean, each of those things on the right is a projection of the state machine.
Okay.
Yeah.
Right.
I mean, that
Right,
translation is
right.
straightforward. He's just going from the automata representation to the regular expression representation.
Okay.
I think the complication will come in because a lot of those actions are blocking actions. So from if you start from a particular initial
No, the
configuration.
problem isn't more complicated even before getting to the blocking actions, because the thing is, computing this
Yeah.
applied to I is not, it doesn't result in a regular language always.
Even if there was no
Even,
blocking.
yeah, actually I'm going to talk about it. I have an
Okay.
example showing that.
Okay.
That's why the complication comes in. So basically, so far, we are not solving the problem. We are just reducing a reachability problem to a new problem, which I call it limit language problem. Does that
I was
answer?
going to ask if this generalizes to multiple channels.
Yes, this is actually the structure. So I, in here, I didn't say it's a single channel. I basically is an expression, a tuple, which represents the initial content for every channel of the system. So reachability is reduced to this new problem, which we call it limit language problem. What does it say? We say we have a language of actions. We have a set of initial channel contents, which is represented by I. We want to compute the result of 0 or more application of L to I. However, this problem is undecidable in general. And I'll show it through this example. That this is, first of all, it's not at all a trivial problem. That's why the whole reachability problem in FIFO system becomes undecidable when we have unbounded channels. So this is an example of a FIFO system with two channels, 0 and 1. We have three actions, three conditional actions. First one says we read A from 0, write A on 1. Second says we read B from 0, write C on 0. And the third says we read C from 0 and write B on 1. So the initial content, channel content we start looking at is AB star empty. So channel 0 has AB star, channel 1 is empty. If we keep applying this set of actions to this initial content, what will happen? First, all A's are transferred to channel 1 based on this conditional action, because it reads A from 0 and write it to 1. Then, every time we hit to a B, first the B is translated to C based on this action, written on the same channel, and after that, all the B's are being transferred to channel 1. So the main question is, let's forget about how to calculate the result, just to see if this language, this limit language, is regular or not. This is a proof that shows this limit language is not even regular. And why is that the case? So if we compute the intersection of this language with epsilon sigma star, the result is epsilon A and Bn. And why is that? We started in the initial channel content with a language which says there are equal number of A and B's in channel 1. We read A's. Every time we hit B, we translate it to C, and then at the end, we're going to keep reading B's. So that means at the end, we have to end up in a language which says there are equal number of A and B's in that channel. This is a non-regular language. So that says the problem, the complication of the problem comes in if we do have even a regular language, regular action language. We start from a regular initial content, still the limit language may not be regular. Another problem, even if we know the limit language is regular, computing it may be undecidable by itself. We may not have any algorithm to compute the limit language. So what have I done? I have looked at a particular class of system, FIFO system, for which the limit language is regular. What is that class of system? First, a short motivation behind how we come up with this class of system. We started looking at the BoxOS protocol, which is the next generation telecommunication services over IP developed at AT&T. In this structure, a call is represented by a graph of features. The features at the endpoint are telephone calls. The intermediate features are telephony features, like call waiting, call forwarding, and so on. The communication between these features are handled by a set of unbounded perfect FIFO channels. In order to manage inter-feature communication, all of these features should implement a particular structure, which we call it transparent box. It's a very simple structure. It has three phases, which is a setup phase, transparent phase, and teardown phase. During the setup phase, basically a feature establishes a connection between its neighbors. Transparent phase, it forwards whatever it received from one end to the other end. And in the teardown phase, it just basically disconnects the connection between two features. Now, looking at the structure of this automaton more carefully, we see the only strongly connected component in this automaton are states with self-loops, which is this state with the linked state here. We come up with a language, which we call it Piecewise Languages, to represent or recognize the language of such automaton. So how does this language look like? Basically, it's a subclass of regular languages. It can be expressed by this expression, M0 star, A0, M1 star, and so on, where MIs are basically a set in sigma, and AI is a letter in sigma or is epsilon. we call a language piecewise if it's a union of simply piecewise languages. So there are some examples here. So A plus B star followed by C is simply piecewise, where M0 is basically A and B. However, AB star is not a piecewise language. We have shown that a language is piecewise if and only if it can be recognized by a finite state automaton where there exists a partial order on the control location of this automaton. So what do we...
Does that partial order have anything to do with the edges? Because, I mean, if I have an arbitrary automata, I can just randomly define some partial order, right?
Yes, but so if you can see in here, if I had a loop back from here, I can establish a partial order between these control locations. For example, just going even here, just go back from n to onlink. Onlink is less than n, and n is also less than onlink.
I see. So you're saying that you will only allow self loops,
yes,
and otherwise it should be acyclic.
Yes.
Okay.
Except our action language is richer because we do allow conditional actions, not just simple read and write.
Okay.
So how can A plus B star be simply piecewise? Because you do need a loop around.
No, it's a non-deterministic choice between a set of letters. So that means analogy with the finite state automata, I have a state with a bunch of self loops.
Okay.
Yeah.
We can have several self loops.
Several self loops, yes. So we define a piecewise FIFO system to be a system where there exists a partial order on the control location of that on its states. So this is an example of a piecewise FIFO system. As you can see, we can establish a partial order in here and say state 2 is less than 1, 4 is less than 2, and 3 is less than 2. However, if we add a loop from state 3 back to 1, we break this partial order because 1 is less than 3 in this pass, and also 3 is less than 1 in this pass. Main observation in here we have is the action languages corresponding to limit language are clean closure of sets of actions. So what does it mean? In here, for example, if I want to compute the all reachable configuration at control location 1, I need to compute the result of applying the process of this action, star of it, to I. So if I do not allow these loops in my structure, whatever I get in this block is always going to be a set of actions, not a regular language of actions, like a string of actions. So we have shown, first of all, if you start from a regular action language and initial regular channel content, still the limit language may not be regular. But if we focus just on piecewise FIFO system, we have analyzed two classes of this system, which is single channel system and multi-channel system. For single channel system, we have shown if you start from a regular initial channel content, the limit language is regular. If you start from a piecewise initial channel content, the limit language is piecewise. In multi-channel system, however, the problem is much more complicated because you already know if you have a regular action language and a regular channel content, the limit may be a non-regular. However, if we have a piecewise initial channel content, we have shown that the limit language is piecewise. Unfortunately, this is one of the cases when I said we know how the limit language is piecewise, but there may not exist an algorithm to compute such a limit language. So we have proven this theorem theoretically, and for particular subclasses of system, we have provided algorithms to compute this limit language.
So you have algorithms for the upper tier?
Yes, single channel, we have an algorithm to compute it. Yeah. So before actually...
What's your intuition that realistic systems have the structure?
So we have looked at multiple domains. Well, the transparent box is one of the main things that how this research started with, which was basically a no functionality, a feature with no particular functionality, and still people had problem to analyze such system because of unboundedness of the queue. The second thing we looked at were session-oriented software, like web services, which is something we're still working on. So the web services, the one that actually be expressed by BPEL processes, most of them have this sort of a structure that they go through a setup phase, then they start being either idle or doing something but inside them, so that we can abstract the whole thing as one state, and then they would basically disconnect the connection between two particular nodes. So most of the session-oriented software can be modeled by this particular class of languages.
So what is happening is that you are throwing away some information.
Yes.
To, like, sort of whenever you have like a strongly connected component, you just want to abstract it away.
But not every time we can do that, because sometimes that may affect the rest of the finite set automaton, the structure of that particular node. But depending on the domain, the ones that we have looked at so far in BPEL processes, most of them have this particular structure that they don't have a memory. It's memoryless. Basically, they start from a node, they just go on and finish at the end. And sometimes they just go back to the first state. So you can unroll it.
So, did you talk to the people who design these thingies? How, when they, I mean, they clearly don't have any tools available to them, so how do they get any kind of assurance that the protocol that they've designed is correct?
So that's actually the big problem, feature interaction problem that AT&T has these days. So that's actually
what do they do in practice?
Testing.
I mean, the engineers are probably,
Testing.
They
do
create
testing.
lots of test cases.
Yes.
But I often, engineers, they write test cases, but they have some high-level intuition of why they think it is correct. Were you able to somehow glean that from conversations with them, why they think their system is correct?
So one of the main things is that, so the whole problem comes in because we have these unbounded channels. Okay, in reality, people come and say, okay, there is no unbounded channel, but the problem comes in when you have unknown delay. That's the way we abstract our model. We say, okay, unknown delays to us is an unbounded channel. So what they do is that they limit they limit the size of the channel in their analysis. They say, okay, if after a certain amount of time we don't receive the message, that means, start again. That means they limit the size of the buffer. But that's the way they test. They limit the size, they put a threshold on the delay, or that means it translated to limited size of the buffer. But in a high level, if you really want to do 100% verification, you can't limit the size of the buffer. You have to actually have this unbounded notion inside your model.
So you said you looked at BGP, right?
Yes.
Does BGP fit into this piecewise?
So that's what we were studying. So we were extending this structure for some time, that adding a very structured kind of loops, but that's still an ongoing research.
But BGP by itself is not
piecewise. Yes, even this structure that I showed you in here, initially it wasn't piecewise. The reason we made it to be piecewise was because by introducing conditional actions, we had loops over here on multiple states. That's why we have a more richer action language, but at the same time, we get the system to be piecewise.
How do you eliminate loops using these conditional actions?
Well, if they can execute atomically. So, for example, here the actual structure is I have two link states, link 1 and link 2. So I read A, go to this state, and then I'll go back to this state. So we basically represent this by conditional action. So because this state doesn't go anywhere else. We can't check deadlock unreachability of that particular state if that's what.
But the thing is that you have lost some behaviors there, right? Because you're assuming that the thing happens atomically.
Yes, we do lose some behavior.
Okay.
But if you look at the TCP protocol, for instance,
yes,
it does have this kind of a structure where you do a lot of things till you come to the established state. And at established state, you're actually focusing off another state issue, because you're looping the established state, but you do a lot of complicated things in the established state. And then you tear off the connection. So it does fall.
I haven't looked at TCP, unfortunately, so I don't have an intelligent answer for that. Okay, so I'll try to just briefly give you some flavor of how we came up with this algorithm to compute the limit languages in multi-channel system. So first, before going there, I define a notion which we call it communication graph. So given a set of actions, we define a graph on this set of actions where the nodes of this graph are the channels and the edges are conditional actions in that action set. For example, if I have this action set with 4 conditional actions, the communication graph corresponding to this action set consists of 3 nodes for channels 1, 2, 3. And for each of these conditional actions, I have an edge to this graph. That means from 1 to 2, I have an edge. 2 to 3, I have an edge. 3 to 3, I have a soft loop on this node. And again, from 3 to 1. We designed our algorithm to compute the limit languages based on the topologies that this graph could have. So we have this state, bunch of self loop on it, which results into a set of actions. In order to compute the limit language corresponding to that set of actions, we need to actually study the structure, how these conditional actions are connected to each other. So we looked at star, tree, and inverted tree and DAG. For the star topology, every read comes from a single channel, which is the origin of the star, and they will write on multiple channels. This is an example starting from a piecewise initial language, which say M1 star A1, M2 star A2. The algorithm computes the limit iteratively. In the first iteration, it computes all channel configuration where the content of channel 1 is in this language. In the second iteration, it computes all channel configuration where content of channel 2 is in this language. And the third iteration, it basically computes all configuration where channel 1 is empty. The tree topology, the main observation is we can basically reduce this topology to a bunch of star topologies. We can partition a tree to a bunch of stars based on the nodes of internal nodes of the tree. That means in here we have 3 stars. The structure of the tree forces a sort of partial order on the nodes. If we order our star topologies based on this partial order, that means 1, 2, 3, and then we apply the algorithm for star topology iteratively, we can compute the limit language for the tree. Inverted tree topology, it's a bit more complicated because so far in the star and tree, we were not reading from multiple channels and writing on a single channel. If we have such a topology, we have to break the topology by introducing shadow channels and then use the tree algorithm to compute the limit and then merge the content of the shadow channels. In here, we said the content of channel 3 depends to the content of channel 1 and 2. However, if you look at the more general topology, which is the DAG topology, we can see in here the content of 3 depends to channel 1 and 2. However, the content of channel 2 also depends to the content of channel 1. That means compared to the inverted tree topology, we are adding another layer of dependence between the channels' content. In order to do that, we basically modify the merge to respect these dependencies between the content of different channels. We have studied complexity of each of these algorithms, and the results of this work was published in FMCAT. In summary, for FIFO system analysis, we focused on reachability problem in FIFO system. We looked at 2 classes, single channel and 3 classes, single channel, multi-channel with acyclic communication graph and general multi-channel. In single channel, we showed that the limit language is piecewise if we start from a piecewise initial language. If we start from regular, the limit language is regular. We have algorithms to compute the limit language, and the complexity of that algorithm is exponential to the size of the initial channel content. In multi-channel with acyclic communication graph, if we
the size of the initial content.
Channel content.
And not the size of the state machine.
No. In multi-channel with acyclic communication graph, if we start from piecewise initial language, limit language is piecewise. For the 2 topology of a star and tree, we know the complexity of the algorithm is exponential. If we start from regular, I had that example which showed the limit language is non-regular. General case of multi-channel system, we know if we start from piecewise initial language, the limit language is piecewise. However, the algorithm to compute the limit still is an open problem. And in general case, if we start from regular, similar to the acyclic case, the limit language is non-regular.
So, I'm still stuck on the exponential and the size of the initial.
Yeah.
So in most protocols, the initial language, initial configuration will have an empty channel, right?
Yeah, okay, but not that. That's not the case always, because you may start from you may start looking at just in the middle of the execution of the system. So you decompose the system that you start from, like, say, okay, I know that I have like AB star in my channel right now, and now I'm gonna start looking at this execution from this point. Not necessarily you always start from empty.
But what happens if your initial channel content is empty? Then you get something very cheap. I mean,
if you have an initial,
in that case?
If you have an empty initial channel content, it's much easier to compute the limit language.
Then the complexity would probably be in terms of the state machine sizes, right?
Yes, but if you remember, the state machine size is not important at this point because we are looking at the limit language problem, not the reachability problem.
Oh.
Reachability is reduced to limit. So for each control location, I'm computing this limit language. Okay. So if I have 10 state, I have to basically
start with an empty channel, right? In one state, as soon as you go to
Yeah,
the
you
next
get next
state,
state, you may start,
immediately
yeah.
have something big. I see. Okay.
Okay, so I have still 15 minutes to actually explain in brief what's the result of parameterized systems analysis we have. Just a brief reminder what we meant by parameterized system, a family of systems where there are n processes executing the same program concurrently. We want to check if a correctness property holds for every size instance of the system. The motivation behind our work is coming from the analysis of famous Lamport-Baker lock. This is a mutex algorithm. The algorithm has a shared lock with two variables. Next ticket shows the value of the next available ticket, and now serving shows the value of the ticket which is being served now. Whenever a process wants to enter the critical section, it basically increments the value of the next ticket. It would wait for this step, and whenever its ticket is being served, it would enter the critical section. Whenever the process exits the critical section, it would just increment the value of the now serving variable. We want to check if no two processes are ever in the critical section at the same time. If you look at the parameterized version of this protocol, we have a bunch of processes, which each of them is implementing the algorithm I showed in the previous slide. They're all sharing the same lock. And then we have unbounded number of these processes in our protocol. Each of these processes manipulate an integer variable, which is the my ticket. So the state space of each of these processes is infinite. In addition, we have another dimension here, which is unbounded number of processes in the network. So we have a parameterized system where each process itself is an infinite states program. The goal is to check safety properties of these such systems, but the main idea behind our approach, we basically adapt some analysis from a single process infinite state programs based on abstract interpretation. We develop a sound, terminating but incomplete algorithm based on AI. The main ideas, we develop a new abstract domain for the analysis of parameterized system of infinite state program. Then we use this new abstract domain in a standard backward reachability algorithm to do safety analysis of such systems. Syntax in our model, we represent a parameterized system by a triple where Q is a finite set of control location, V is a finite set of variables, and T is a finite set of rules. The rules basically say process would go from control location Q to Q prime based on a guard. We allow for three kinds of guard: local, universal global, and existential global. In local, we check the local variables of each process, and we change local variables of the same process. Universal global transition goes through if a condition is true for all other processes in the network, and existential, the transition would go through if the condition is true for just some processes in the network.
I just wanted to suggest, because we interrupted you so much, you don't have to finish in 15 minutes.
Oh, okay, so I shouldn't run through it. Okay, good.
You can take 5-10 more minutes. Mother, is that okay?
Yeah.
Thanks for that. Okay, so this is basically an example which shows a parameterized system, the model that we have looked at in an action. So this is an instance of a parameterized system with just three processes: process P1, P2, P3. The transitions of these processes are labeled by these guards. G1 is a local guard, G2 is a universal guard, and G3 is an existential guard. Each of the processes manipulate an integer variable, which is x. In the initial state, we assume all processes are in control location 1. Initial value of x of process 1 is 2. Initial value of x of process 2 is 0. And of process 3 is -1. In a possible execution, process 1 would take the transition, goes from state 1 to 2. And according to G1, it would increment the value of variable x of itself. So x would become 3, and the rest would be the same. Continuing with this, in this execution, we are looking at this process P1 would go from state 2 to 3 if, according to G3, there exists another process in the network where its control location is at 1. The difference between the value x of this process and that other process is greater than 2. And if that's the case, nothing would be changed for the x of the self process. So in here, P3 is such a process because it is at control location 1, and x3 and the difference of my x, and that, which is 3 and minus 1, is greater than 2. So the transition would go ahead, and this can go and continue. In another execution, again, we assume all processes are in control location 1. However, we assume different values for x. Again, according to G1, process P1 would go to state 2 by incrementing variable x. However, this time, it could go to state 4 if, according to G2, all other processes in the network, which are process 2 and 3, are in control location 1, and the value of variable x of those processes is greater than 1. Looking at this state, we can see this transition can go ahead based on these constraints. So actually, before going further, looking at these global states, we see it consists of two parts. One is the control location part. The other is showing the value of variable x's of these processes. In order to capture this information, we design an abstract domain. First, just to capture the control location information. We call this domain parametric domain, which basically just looks at information about the control location of the configurations in our parameterized system. For example, here, S is an abstract element in our abstract domain, which represents all concrete configurations where there are at least 3 processes, 1 at Q1 and 2 at Q2. One caveat of this is that process names are not important because you're looking at a parameterized system. So in here, T would say the same thing. There is only 1 process at Q1. However, this time we call it P2, and it says there are 2 processes at Q2. As you can see, these 2 abstract elements using different process names. However, both of them would say 1 process is at Q1 and 2 processes are at Q2. These two abstract elements represent the same abstract element in our abstract domain. However, parametric domain do not capture anything about the data value of the processes. We extend this parametric domain using an existing numeric abstract domain. For example, here we are using octagon, where the constraints are represented by this form. And this global state in our abstract domain says that there are at least 3 processes, 1 at Q1, 2 at Q2, and the value of variable x of process P1 is less than the value of variable y of process P2. So as you can see, we are actually getting one existing numeric abstract domain and adding it to the parametric domain that we already had. In here, we are using octagon. You can use polyhedra or any other existing numeric abstract domains. We have the same thing as before, that process names are not important in this abstract domain. Again, T and phi representing S and psi, representing the same thing as S and psi. And however, as you can see here, the constraints have different namings at this one, but they match with what process is at what control location. So similar to standard abstract interpretation sort of work, we have this abstract domain. We developed, we showed soundness, like a soundness relation, like preimage, and all of the other operators for this particular abstract domain, which the details are in our paper.
But in this abstract domain, the number of processes seems to be finite. You have to deal with unbounded number of processes, right?
Yes. So we use this abstract domain to represent this system. Okay. And then we develop a standard backward reachability. We do backward reachability. What does that mean? We start from an error state. The error state would say 2 processes are in the error state. We do backward analysis. So we sometimes going to just stick with that number of processes in our network. Because the abstract element would say there are at least 2 number of processes. So maybe there are n number of processes in the network. So as you can see, this at least is the tricky part here.
Oh, at least. Okay, you're saying that there's a bunch of other processes there, and you're not saying anything about them.
No.
You're doing whatever the hell.
Yeah, and I do backward reachability. So I start from a concrete configuration which says, okay, I have 3 processes.
Yo.
And then I compute the preimage of that, and the preimage of that, and the preimage of that.
But what I don't understand is that when you compute the preimage, right, it could be that the transition could have been executed by one of these other guys that you did not model, right? Then what happens?
Exactly. That's why our backward reachability may not converge, because we may end up adding new processes. as a witness process. So as you can see, so my guards were existential or universal. With universal, I would say whatever I see so far, then I define a guard on that. But when I have an existential guard, I would say, okay, this transition would go ahead if there exists such a process in the network. When I do backward, I may always have such a witness process. That means I may end up adding processes in my configuration. And that's one of the reasons that our algorithm may not converge. Okay. But there is also another reason the algorithm may not converge. We have this numeric abstract domain. So the algorithm may get stuck in a loop of, like, because of the numeric abstract domain we are having. So, but that's easy because we have abstract interpretation. There are approaches to solve that problem. So what we do, we basically use the widening operator of the numeric abstract domain, extend it to our parametric domain. So we define a new widening operator for this domain. But the other problem is coming from the successive application of pre-image to a transition with existential guard. That means every time we do the pre-image, we add a new process. So we may end up adding unbounded number of processes to our configuration. For that, we design an extrapolator operator, which basically compute an over-approximation of that configuration by dropping some processes from the configuration we are looking at. So for the main problem, first problem, numeric domain may be infinite. We have the widening. For the other problem, we have the k-compact operator.
So I have a question on the previous slide. So when you talk mainly about some of the processes, how do you execute universally guarded transitions?
So that's one place that over-approximation comes in. We assume if at this state, like this is a configuration, when we do the pre-image, we are assuming these are the number of processes we have in the network. So if we do have another process which is violating the case, we are doing over-approximation of the system. So actually, the place where over-approximation comes in is because of the universal guards. But the divergence comes from the existential guards. Does that answer your question? So now, using these two widening and extrapolator operator, we have shown the backward-reachability algorithm would terminate, and it always returns an over-approximation of the set of backward-reachable configuration from the error configuration. So in summary, for parameterized system, we looked at safety property analysis for a parameterized system where each process itself is an infinite state program. We take advantage of abstract interpretation, and we developed a new abstract domain where which represents a lower bound on the number of processes at a control location. It employs a numeric abstract domain to capture arithmetic relations between the variable of the processes, and our abstract domain is generic enough to be instantiated by different existing numeric domains like octagon, polyhedra, and other things. We have developed extrapolator operator for the domain to guarantee sound termination of the backward-reachability algorithm, and we have actually implemented this algorithm to check the mutual exclusion property of the algorithm I showed at the beginning of this part of the talk. So, in conclusion of the whole thing I have done in the last couple of years, by now I think everybody believes, and even before that, believe that concurrency is everywhere. It's hard. Implementing, debugging concurrent software is very hard. So in the last couple of days, I have looked at algorithmic techniques for the analysis of concurrent system. In FIFO system, I looked at reachability. We looked at a particular subclass of FIFO system for which the problem becomes decidable. However, for parameterized system analysis, we take another approach. We developed a semi-algorithm to compute an over-approximation of the system for safety analysis. So what I am interested to work on, because of mostly my broad background in both dynamic and static analysis of concurrent system, these days I'm very interested to actually combine the approaches from static and dynamic analysis together, because we know static analysis is hard, complexity is high, but however we can extract some information from the dynamic analysis of the system in order to reduce the complexity of the analysis in the static-based analysis. So this can actually, coming from the statistical analysis of the data collected during monitoring, in order to basically reduce the complexity when we are using standard static analysis for concurrent system. Thank you.
So you pointed out one of the problems you looked at, which was the box OS
Yes.
linking algorithm. And Manan also pointed out BGP and asked if that was an instance of these things, of some of the problems that you're looking at. How often is it that you find like a random developer in a company come across this kind of concurrency problem if they just want to add threads to their application? Like, is it like for some big product like SQL Server, you're going to find like in the kernel there's one big problem that's addressable with these situations, or is it everywhere?
So, so when we started this research, I actually just knew about AT&T. And then when I started presenting some of the results that we have here and there in conferences, then I actually was amazed myself to see that people come to me and say, no, this is not that limited as you can see, because there are processes that, there are systems that have this sort of restriction on their structure. And that's how actually we got into web services. That wasn't something that actually we came up with. Somebody pointed this out to us, that they had exactly the same problem, that they were looking at web services communicating over unbounded channels, but they couldn't do reachability because of the unboundedness of the channels, and they were doing some sort of bounded size channel analysis on those sort of systems. So what I think in general is that I can't say that this restriction that we have is it's everywhere. It happens in every application. But the thing is, depending on the property you're looking at and the particular application, you may be able to model the system in a certain level that actually happens to have this sort of structure. That was the main problem we were looking at BGP, because BGP itself, each process, it's hard to model even each process as a finite-state automaton. So they were doing like the people we were collaborating with, they had particular abstraction to actually model one node in BGP by a finite-state automaton. Then we were looking at to see the behaviors of this particular automata, if we can abstract it to somehow to satisfy the restriction we have. So I don't know if I'm actually answering your question. Is that, yeah? Okay, good. So because, so this is something that I think, depending to the application, we can massage the actual structure of the automaton and see if it fits our structure or not.
So you said you had an algorithm for verifying the box OS protocol.
The particular feature I showed you, yes.
Implement it?
Yes, we can implement. However, the problem in here is that the algorithms to compute the limit showed you the complexity is exponential in most of the time. So we had implemented that for single channel system. And but for multi-channel system, for the star and tree topology, we still have exponential blob, but with the inverted and diag, which is usually the sort of structure you get if you have a very multi-connected feature between a bunch of other features, then the complexity is not nice. So we actually realized that it's just doesn't work to implement it. So because of the performance.
So I have a question.
Yes.
I don't really have a question. It's just that I wanted to raise a certain issue for discussion. When you try to build verification techniques which are completely automated, where the worst case complexity is really, really high, I sometimes feel that effort is not justified. If there's a programmer and the programmer wants to do verification, where there's a very high chance that you can prove the absence of bugs, then I feel that the programmer should do some work, some extra work. Otherwise, all the programmer should get is some bug hunting with the relatively low complexity. And the reason I say this, the reason I submit this to you, is that I find that in a lot of these sound techniques, in order to get decidability and low complexity, you have to put in so much restriction in the model that it becomes not reusable. So it becomes very specialized to this guy's problem or that guy's problem, right?
Yeah, that's absolutely correct. Yeah, I completely agree with you, because from theoretical perspective, it's interesting to see what's the worst case complexity of the whole thing, and then usually, as you say, it's hard, it's not nice, and but at the end, when you start looking, when you tell the programmers that if they want 100% verification, they have to accept the complexity of the program and the whole verification procedure. But otherwise, I personally think in these sort of algorithms, even average case, the complexity for average case maybe makes sense more than the worst case complexity. For example, in the ones that the FIFO system we were looking at, we were saying that it's exponential in the size of the initial content. And then we were looking at a complicated regular expression. But that's not even the case in average case when for the particular application we were looking at.
But what I'm wondering if it's possible to drive the complexity down and make the result more general if you don't insist on full automation. Where you say, okay, you
full
guys
automation or
give us
sacrificing
some,
sacrificing the verification purpose or
no, I mean automation.
Automation.
You still get, if you want 100% soundness, then apart from providing the system description, there must be, is there something else that the programmer can provide that will make the verification less complex and also the method, the verification method, more generally applicable? You see what I'm asking? It's a sort of slightly different kind of question.
I'm not sure if I'm actually, I think I got lost a bit in this discussion, so.
Well, we will have
can, yeah,
yes.
Okay, great.
So I also have another challenge to put forward to you. So you said you verified Lamport's bakery algorithm.
Yes.
So Lamport also has another algorithm that's very popular. It's called backsource. And apparently somebody told me that they found a bug in Lamport's algorithm, which is amazing. But you need more than 5 processors to find the bug.
Okay.
So the challenge to you is, can you?
Yeah, I have to look it up. That's interesting. Sure.
Yeah, it's a challenge for you to think about.
Yes. Thanks. Yeah, sure.
Great. Let's thank the speaker again.
Thank you.